Hola a todos, ¿qué tal? Bienvenidos al seminario de álgebra. Entonces, el día de hoy nos va a presentar Ville Salo sobre Groups of Multidimensional Cellular Automata. Thank you very much, Ville, and we're looking forward to your talk.
Ok. Gracias por la invitación. Mi charla es sobre grupos de automorfos de subshifts. No, it's not actually in Spanish, but I felt like saying it.
Grupos de automorfismos, we can say.
Was that
Yes.
correct? Yeah, grupo de automorfos. Yeah. But so, in other words, these are groups of multidimensional cellular automata. And so this is specifically reporting some results of mine from spring, in fact, this year. And these are solutions to some problems of Hochman and Barbieri, Carrasco Vargas, and Rivera Bustos, which I will tell you in a moment. And yeah, so I have a paper on this on arXiv and submitted somewhere. I'm presenting not every result from the paper, but sort of a subset of it, which I think will be a bit nicer not to have to rush through all the stuff, because there are a lot of technical things. I will want to present the main contributions. So let's start with some definitions. So let's have a finite set A. I will call it the alphabet. Okay, and then you have a group. So the group is always going to be infinite. And it's going to be finitely generated. And specifically, it will be generated by a finite set S. So in other words, every element of G can be written as a product of finitely many elements from this set S, or their inverses. I will directly assume that S is symmetric, meaning that S is equal to its inverse, by which I mean this set. Well, so this is the problem with open board today, that for some reason it's not drawing all the short lines, but I will, yeah, so now it's getting worse. Okay. Well, I will try to keep my lines long and then it will work. Okay, so I will assume this, and maybe I'm not even sure if I want to include the identity in my S, but okay. So that's my assumptions. And so you can keep in mind the case where G is either Z or Z squared, or more generally this Z to the D. So in this case, it's very natural, of course, to take S equal to the natural generating set E1 plus minus 1, E1, E2 plus minus, yeah, so this is the, yeah, sorry about this. I don't know why this is happening. Yeah. Okay, and so on. And here, of course, EI would be the vector where you have I minus 1 zeros here. I'm sorry, I minus 1 zeros, and then you have 1, and then you have zeros. Okay. So that's a good example. And then the only other example I will mention is the free group, but I will not really talk about the free group. But in case you know the free group, that's another interesting example. So, so there are kind of two layers of groups in this talk. So, the groups of multidimensional cellular automata will be something we sort of build on top of this group G and the finite alphabet. And so the G here will be the multidimensional. So actually we will more generally talk about cellular automata and groups. And when the group is Z to the D, then we talk about multidimensional cellular automata. So you should think of this G as the sort of geometric group, and then the groups of cellular automata are something that acts on these, acts on configurations on that geometric group. So for G, we like to think of its Cayley graph, which is defined with respect to a generating set, and it's the graph where the nodes, it's the graph with nodes G and edges from G to GS, where S is in S and little g is in the group G. So for example, the Cayley graph of Z squared with respect to the S I mentioned up there, which would be E1, well, plus minus 1 to be careful. Where am I? So this one would look like this. So you have a grid, and okay, there are sort of two dual points of view, but the natural way in the graph formalism, what? So it's the natural way to think about it in the graph formalism is that at the nodes you have 0, 0, 1, 0, and so on, and going up here you would have 0, 1. So in the graph formalism this would be natural, but actually because I want to put some letters on the group, it's also natural to think of it as you might think of like a chess grid or something where I have squares for the group elements. So in that case, one of these squares would be 0, 0, and the square on top might be 0, 1, and this would be the square 1, 0, and so on. So that would be the Cayley graph of Z squared. And in the case of the free group, which I will occasionally mention, the Cayley graph of the free group would be this infinite tree. Maybe you have seen this thing. Okay. Anyway, I will not talk much about that, but just in case. Okay, so what is the object I want to construct? Well, I want to talk about groups of cellular automata, and groups of cellular automata are actually automorphisms of a certain dynamical system, namely the full shift. So we consider this dynamical system where, so a to the g is just the set of all functions. Actually, I like to call them x, my configurations. And the configurations are precisely the, they are the configurations are functions from the group to A. So you can think of them as being assignments of letters to the Cayley graph. So for example, in the case of Z squared, where we had the Cayley graph like this, if A is, for example, equal to 0, 1, then an element of A to the G might look like this. So I haven't drawn the numberings, but if you pretend that this is the origin, for example, then at 0, 0 you would have 0, at 1, 0 you would have 0, and at 1, 1 you would have 1, and so on. Okay, so that's the set of configurations. And I call this the full shift. I will not go into why it's called the full shift, but maybe you can guess, because we define something called the shift map on it. So, by the way, if you don't know this notation, this is notation that means that G is a group and it's acting in some way on this set. And the action is defined by the following formula. If you have a configuration X, so an element of the full shift, then you get another element of the full shift, which is defined by this formula here. So what does that mean in practice? Well, for example, if I have my, well, let me maybe draw this again. So I have some configuration on let's say this belongs to 0, 1 Z squared. I'll just put something random here. Then let's call this X. Then what would be 1, 0 of X? Well, the action here is pushing. So even though there's a G to the -1, it basically means that you're pushing this configuration in the direction of the acting G. So this is the G and this is the X. So that would look like this. You would put here in the second column this first column from here, so 1, 0, 1, 0, and then this column would be moved here, 1, 1, 1, and then this column would be moved here to 0, 1, 0, and then here you would copy from the left. So that would be what 1, 0 of X looks like in this situation. So that's the full shift. And now that we have the full shift, what else do we need? We need a topology on it. So this thing, the full shift with the G action, is a compact dynamical system. Let's just say it's a dynamical system. What does that mean? It means that the space is compact metric. Actually, it's a contour space. So by the way, if you don't know what this means, compact and metrizable, these are basic definitions from topology, and the contour space is also a definition from topology. If you don't know what that means, it doesn't really matter, but because I will also define concretely my objects a bit later. Acts on A to the G by homeomorphisms. Okay. The specific topology that we put on A to the G is the product topology. So A has the discrete topology and G also has the discrete topology. So that would mean, and the metric is that two configurations are close if they agree in a large ball. So we say dxy, if x and y are in this A to the G, then the distance is small if x agrees with y in a large ball, and maybe so there are many ways to quantify this precisely. You can the point is that as long as when r increases, this starts implying a smaller and smaller distance between x and y, then you get the correct topology. Let me define the notation. So BR is precisely those elements of my group G which satisfy that the length of this with respect to the generating set S, recall that we always fix some generating set for the group, that this is less than or equal to R. And XBR is the restriction of X to BR. So that would be, so basically this means that X and Y have the same contents in a large ball. So for example, in this previous slide, a configuration would be close to X if it contains these 9 symbols here, and if it also contains the next symbols here, then it would be equal to X in an even larger ball. So it would be even closer to X. Okay. So now that we have a topology and we have an action of the group, we can define the endomorphism monoid. What is the endomorphism monoid of this system? It is the set of all functions from A to the G to A to the G such that f is continuous. By the way, if you have any questions, I'm happy to answer during the talk. I don't have a full plan of what I'm gonna say, in fact. So so if something is strange, it's probably because I've forgotten to say something. So don't hesitate to ask. So the endomorphism monoid would be all the functions which are continuous and they commute with the shift for all G in the shift group, in the acting group, like this. So a couple things. This is a monoid under composition, under function composition. So why is the monoid? Well, in a monoid, the only thing we have to check is associativity. Well, that's obvious from the fact that function composition is always associative. And then we need to check, well, we need to check that composition is even well defined. So if you take two continuous functions which commute with the actions and you compose them, well, the composition of two continuous functions is well known to be continuous. And then if both f and f prime commute with the shifts, then you can do this calculation where G jumps over first F, and then it jumps over the other one. Okay, so this proves that it's actually closed under function composition, and then you also have to check that there's an identity element, and it's easy to check that the actual identity function is an identity element of this. And now, when you have a monoid, you always have a group. You have the automorphisms, which are those F in the endomorphism monoid, which have an inverse. What's going on? For some reason, I cannot draw this low. Okay, let's say they are all the endomorphisms such that there exists an inverse endomorphism. There exists a... I have to continue here. Okay, I have to... Sorry about this. I don't know why OpenBoard is acting so badly today. Maybe this is there's the bar for sharing the talk on the bottom, so maybe that's the problem. Yeah, so F is in end, and there exists another G in end. Now G is not a group element. Sorry, maybe I should write F prime, such that F circ F prime equals F prime circ F equals the identity function. So that would be the automorphisms. So in every monoid, you always have a group obtained by taking the invertible elements like this. Okay. So a couple of things. There's a very concrete way to see the endomorphisms. So F belongs to end if and only if F is a function from here to here, and there exists radius. So the radius would be a positive non-negative integer, and there should be a local rule which goes from A to the BR, so the ball of radius R in the group to A, such that F of X at G is obtained precisely by applying the local rule to G to the minus 1x at BR. So what does this mean in practice? Well, again, I will just look at the Z to the 2 Z squared example. So it means that you have some rule which takes the configuration here. So you have some symbols here. So an endomorphism would be something that, to determine the new symbol here, it will look at some neighboring symbols, and then it uses some local rule. It can be an arbitrary rule, and this local rule tells you what you write next. So you feed this pattern into the local rule, and then the local rule spits out some new letter F as a function of this pattern. And the point is that you apply this the same way in every position of the group. So here, for example, to determine C, you would apply the exact same rule to this pattern, and then that pattern would spit out the new value in here. So that's the not a very clear picture, but hopefully it was clear together with the explanation. So that's in any case, that's the formula defining the local rules of endomorphisms. By the way, this might not look like you're applying the local rule at G, but the point is that what is G to the minus 1x? Well, because of the definition of the shift, this is more or less the same as the contents of x at G BR, but then we cannot apply the F-lock to this pattern because the domain is G BR instead of BR, so we have to translate it, and it's easier to translate X instead of trying to translate the pattern. Okay, but anyway, so local rules exist for endomorphisms, and this is an if and only if. So all the endomorphisms come from this construction. So this endomorphism monoid has been studied by several people. I think Alonso has multiple papers on this, and I also have some results on the endomorphism monoids. But today we want to concentrate on the automorphism groups. So you cannot really say actually much more immediately about the automorphism group. The automorphisms are just endomorphisms, so they have local rules, but it's not sort of immediate. It's actually very complicated to tell typically whether some local rule defines an automorphism or whether it defines a non-invertible cellular automaton. For example, in 2 dimensions, if the group is z squared, this is undecidable. There is no algorithm that tells you whether you are an automorphism. You can say the following, that or maybe I should say the following are equivalent. For f in the endomorphism monoid, the following are equivalent. 1, f is in the automorphism group, so it has an inverse, which is also an endomorphism, and that f is a homeomorphism, and finally that f is bijective. So for topological reasons, all of these are equivalent. So if you're an automorphism, obviously you are a homeomorphism and you are bijective. By the way, homeomorphism means continuous forward, and the inverse is also, it means a bijection, which is continuous, and its inverse is continuous. So an automorphism is by definition a homeomorphism, and by definition that's a bijective map. And it turns out that if you have an endomorphism, which happens to be bijective, then it's even an automorphism. Okay, and then what did I want to say next? Sorry, now I write. So I was gonna write G here. That was yeah. Okay, so this you can say. So now, what do we want to say? Well, now I want to tell you a few classical results. So there's a theorem by Kim and Rouge from 1990, which is the following. The automorphism group of 0, or let's say the automorphism group of A to the Z, so just one-dimensional cellular automata. Oh, maybe I should have told you that something that I mentioned on the first slide, I guess, but is also the group of cellular automata. So the reason I call it automorphism, the reason I like to call it an automorphism group is that there is a more general object where this A to the G is replaced by some dynamical system, and you can talk about the automorphism groups of other dynamical systems as well. But especially in this full shift case, we tend to call it the group of cellular automata because it exactly corresponds, in particular in this case, A to the Z or A to the ZD, it corresponds exactly to the classical notion of cellular automata. Okay, so there's this theorem of Kim and Rouge, which says that the automorphism group of A to the Z embeds in the automorphism group of B to the Z for any alphabets, as long as the alphabets are non-trivial. Okay, so my alphabets are always finite. As long as you have at least 2 letters, then these embed into each other. By the way, when I write this, I mean embed abstractly. So there's no, so even if A is a subset of B, then the inclusion map is not an embedding, but actually it's even meaningless. But they embed it abstractly in the sense that the automorphism group of A to the Z is isomorphic to some subgroup of the automorphism group of B to the Z. And now there's this old open question by, I think, Boyle, Lind, and Rudolph, whether the automorphism group of the 3 shift, so 0, 1, 2, is actually isomorphic to the automorphism group of the 2 shift. So that's open. By the way, just to check, are you guys hearing me still?
Yes, we're here.
Yeah, great. So just so I'm not talking to myself.
Yes, great. No worry. We hear everything. Yes.
Yeah, great. By the way, can you see my mouse moving?
Yes, yeah, we can see it.
That helps.
Yeah.
Helps probably because I'm using it. Okay, so that's an old question, and now there are a couple of more recent questions. So there's a question by Hoffman. Maybe I will first mention his slightly earlier question. I don't remember where this is from, but so he asked whether the analog holds for higher dimension. So that's a question. We don't know if there are actually any non-trivial embeddings. So in some cases there are. If A divides B in cardinality, then there's a sort of trivial embedding. But the question is whether there are any non-trivial embeddings between these. So this is still open, and I will not answer this in the talk. But Hoffman also has this variant. So of course the direct generalization is to compare alphabets like in this theorem of Kim and Rouge, but you can also compare the dimensions. So he asked this question. Maybe I'll write it the other way around. So little d for the smaller one. Okay. So his question was, are there situations where the automorphism group of a higher dimensional full shift embeds into a lower dimensional one? So basically, can the group of can the group of uppercase, but maybe we can just simplify it to d plus 1 because it's more or less equivalent. Let's write d plus 1 here. Like this. So does the group of d plus 1 dimensional cellular automata ever embed into the group of d-dimensional cellular automata? So he asked this question in 2017 and in a conference, and he has a couple of papers with related questions. Okay, and then there's another recent paper by Barbieri, Carrasco, Vargas, and I think Rivera Bustos. And this is from this year. And they asked whether the automorphism group of A to the F2, so the free group on 2 generators, and you take the full shift on that, and you take the automorphism group. So basically, reversible cellular automata, which act on configurations of these infinite trees, for the free groups. They asked whether this embeds in the automorphism group of B to the Z, or any alphabet, and any interesting alphabet B. So I proved the following. Well, I proved the negative answers, but maybe I will just write no to both. This is due to me, and of course from I wrote 2020. This is not 2020. This is sorry, the year is 2025. Oops. Yeah. So actually the story is kind of funny, because before I proved this, so Sebastian sent me an email about this question, and we both agreed that there was basically nothing we can do about Hoffman's question, but here we thought that there might be something to, or at least I thought there might be something to do, because we know that the word problem of this group here is in co-NP, and in this group we didn't know the complexity. So I proved that, in fact, I proved that this automorphism group of A to the F2 has p-space complete word problem. So I don't want to talk about that too much, but this is what I proved first, and this proves, because we suspect that p-space is harder than co-NP, this would prove sort of conditionally on some complexity theoretic conjectures that this does not embed. But then Barbieri kept bugging me about whether I can improve this, and finally I came up with another method, which is unconditional. And this method uses something called residual finiteness, which is the topic we're going to go to next. If one of the following holds, so I'm going to, so these are actually three equivalent things. For all G not equal to 1, the identity element, that's right, E of X for the identity element. So G is in uppercase G. There exists H of finite index. So the index is just the number of cosets of the subgroup, such that G does not belong to H. Okay, so that's one of the equivalent conditions. Another one is that there exists that for all elements which are not equal to G, oops, not equal to E, there exists H, a normal subgroup. So recall that a normal subgroup is a subgroup which is closed under conjugation. So this means a subgroup, and it means that G H G to the minus 1 is equal to H for all G in G. So that's the definition of normal. And then the same. Okay. So what next? Oh, and G is not in this subgroup. Then the next one, for all R, there exists a normal subgroup such that actually BR embeds in the projection. I will explain what this means. Okay, so if you have a normal subgroup, then you can define the quotient group, and you have the natural map where G maps to GH, the coset, like this. And from normality, it follows that this is a group homomorphism, because if you take this to G and some G prime, then you get G H G prime H, and then because of you can conjugate the G prime on the other side to get a coset. So if H is normal, then this is a homomorphism between groups, and BR embeds means that let's call this phi, then phi restricted to BR injective. So BR embeds in the projection meaning that the restriction is injective. So these are equivalent things to residual finiteness. So in words, it means that finite quotients, let's say enough finite quotients exist. That's sort of the slogan for residually finite. So now we can prove the following: if G is residually finite, then the automorphism group of A to the G is residually finite. So by the way, I forgot to say what I'm going for. The plan is to outline the plan for the rest of the talk is to outline why the automorphism group of A to the Z to the 3 does not embed in the automorphism group of A to the Z. I don't think I will manage to outline this very far, but I will maybe manage to say something about that. Maybe I will explain. Well, we will see how far I manage to go. But the first observation and the whole point of this is to observe that these groups are residually finite. So if the geometric group G, on which we have our cellular automata act on, if this is residually finite, then also the automorphism group is residually finite. And this I can prove. Okay, so how do we prove residual finiteness? It suffices to check the first one. So we take a non-trivial element, and we need to find a subgroup where it does not embed. Actually, I guess I will immediately show the second one. I will find a normal subgroup where it does not embed. So let's have a non-trivial automorphism. So of course, any trivial element, the trivial element will of course be in every subgroup. So we will take a non-trivial one, and we recall that F has a local rule. It has a radius R, and then it has this F block, which is its local rule, and it goes from A to the B to the BR to A. Okay, and now since G is residually finite, we can apply this third condition. We can find a normal subgroup such that BR embeds in the projection. So I don't want to give you the exact definitions, but I want to say the following. There exists a normal subgroup. Actually, I don't even need it to be normal. Such that such that there exists an H periodic X in A to the G such that X restricted to BR equals P. I forgot to for any P in A to the BR. Okay. So what is that saying? If you take any P in A to the BR, so that looks like this. You have in the group G, you have this ball of radius R, it's the BR, and then you have any pattern here. So you have some symbols A's, B's, and C's, and B's, and A's in this ball. Then residual finiteness means that we can find a finite index subgroup, even normal, so that you have a periodic element. So you can find a subgroup like this, which looks like you have the identity there, and you have H1, H2, H3, and so on, and so that the balls are actually disjoint. Okay, so in the case of, maybe I will show you what it looks like in the case of Z squared. If in Z squared you have a ball, so actually with my metric the balls are D1 balls, so they actually look like this, but we can just draw them as balls. So for Z squared it looks like this. If you have a pattern, so this would be in A to the ball of radius R, then we would take the lattice. We would take the lattice of 0, 0, and then we would take let's say 0 and minus n. Then we would take in here we would take n and 0, and here we would take n and minus n, and so on. So we take this very sparse lattice, and then we copy this P in all of these positions. And this will give us a periodic configuration where this P appears at the origin. Maybe I need to define what it means to be H periodic. So X is X periodic if and only if Hx equals X for all H in H. So that means the same as saying that Hx at G is the same as I cannot draw this low again. It's the same. Recall that Hx at G is the same as X H minus 1G, and this has to be the same as Xg for all for all x. So h periodicity means basically that if you multiply the coordinate from the left by h prime, then it stays the same. So you can really actually think that this is another definition of residual finiteness. Residual finiteness is precisely equivalent to the fact that in a full shift over the group, for any finite pattern, you can find a periodic configuration that contains this at the origin. Okay. So now how do we use this? So the point was that this F was a non-trivial automorphism, and it's defined by this local rule. So the local rule has to be non-trivial. Okay. So it means that F log of some P is not equal to the central element of this P, or some P in A to the BR, right? Because if it always just copied the central letter, then no matter what configuration you apply it to, it would just write the same configuration. So actually, it would be the identity map. So this has to happen for some P, and now you pick X, H periodic. Now you pick H of finite index. Finite index such that there exists H periodic X with X. By the way, W slash means width. I guess I've used it many times now. So you take a pattern which in BR contains P, a configuration which contains P near the origin, and it's H periodic. Then you have that F of X is not equal to X. Why? Well, because since actually Fx at E equals F log applied to X dr, which is not equal to Xe. So in particular, these are not the same. Okay. So now you define P of H as the set of H periodic configurations. Okay, so all the configurations Y, which are H periodic, so shifting them by H with a fixed system, then actually the restriction of G to this set is well defined. So G of PH is PH. So why is that? Well, in general, if you have a group action which commutes with, sorry, I should. This is not good. That's not what I wanted to write. So sorry. G does not fix this set, in fact, but the automorphism group fixes it. Okay. So if you have an automorphism and you apply it to an H periodic point, then because it commutes with the shifts, then the image must also be an H periodic point. So the computation is easy if X belongs to P of H, and F is an automorphism, then F of X is in PH, because if you shift it by H, well, F commutes with H, so you get this, and this is just F of X. So you get that F of X is also H periodic when H belongs to uppercase H. Okay, so this is a finite set. So that means that we get a homomorphism from the automorphism group to the symmetry group of PH. And this is finite. And this homomorphism maps F to something other than the identity permutation. Why doesn't it map it to the identity permutation? Well, because we concluded that for this H periodic point, it does not map to itself. Okay, so we conclude that if G itself is residually finite, then the automorphism group is also residually finite. Okay, so then the final thing to note for one direction is that there is a quantitative version of this. So if G is residually finite, there is the systolic growth, which is defined as follows. The systolic growth is a function that at n takes the value which is the minimal index of a subgroup H, such that H Bn does not intersect H prime Bn, or H and H prime in H, and H not equal to H prime. So basically, one of the definitions of residual finiteness was that the systolic growth is finite. You always find some finite index subgroup where this kind of thing happens. I'm writing it a little differently here, but still. Then there's also the residual girth. This is systolic growth, residual girth. I will not write the full things, but this is exactly the same thing, but H is normal. So you have to find a normal subgroup H such that the same happens. Okay. And then you finally have the residual finiteness growth, which is the minimal. So it's the maximum over the ball of radius n of the minimum of this kind of index, such that H again is normal, and this particular element does not embed. Embeds. So G is not in this group H. This should not be the identity element of G. Okay, so you can easily check the following. The systolic growth is less than or equal to the residual finiteness growth, and the residual finiteness growth is also less than or equal to residual finiteness growth. And I will define another thing, which is something called the simplistic growth. So let's write simp G of n is the minimal, is the maximal maximal cardinality, max of the cardinality of a group which is simple. H is a subgroup of G, which is simple, and H contains some G with less than, contains a non-trivial element G, whose word norm under the generators S is less than or equal to n. Okay, and you can check that this simp is less than or equal to RFG. So in particular, it's less than or equal to RG. Okay, so now we have the following lemma. If the systolic growth, actually I can directly write the formula. So the simp of the automorphism group, so sorry, let's write it like this. If let's say G is finitely is a finitely generated subgroup of odd A to the G, then the simplistic growth of G of this math the calligraphic G, is less than or equal to the exponential of the systolic growth of G. Okay, so this may look a little complicated, but where does it come from? It's actually proved exactly here. So what did we do here? Well, we had some non-trivial element. If we suppose that this element has radius, it has word norm n in some finitely generated subgroup, then that tells us a linear bound on this R. And then when you go through this argument, you observe that the systolic growth tells you how large this period has to be, and then actually it turns out that this group is of size So because the point is that the number of periodic points is about exponential in the systolic growth. So the size of this pH is about exponential, and therefore the symbolic, therefore the symmetric group is about exponential in the exponential of this size of the size of the ball, which is the systolic group. Yeah, so something like that. So basically the proof I gave, just the quantitative version, gives you this crazy formula. So next, let's apply this. What is the simplistic growth? What is the systolic growth of z to the d? Well, if you think about what is the systolic growth is, you take a ball of radius r, and you want to find the smallest possible index of a subgroup so that these balls around the elements don't intersect. Well, I already gave you the proof that if you just take the lattice where the separation is let's say 2r, then the balls do not intersect, and then a counting argument shows that this is a direct calculation shows that the systolic growth is about n to the d. So that was sys zd of n is about n to the d, and therefore actually the simp of ought a to the z to the d of n would be less than or equal to exp of z to the d. So by the way, when I write less than or equal to, there are some I don't literally mean less than or equal to. There's a sort of equivalence relation you have to quotient out by. Okay, but then we have another theorem saying the following, that the simplistic growth of the automorphism group almost reaches this. So this is actually more than or equal to exponential in the exponential, and then you have n to the d divided by log n. Okay, so the upper bound is a double exponential in z to the d, and then the lower bound is exponential in n to the d divided by log n. So I didn't really have time to go to the proof of the lower bound, so we can just conclude the. So then I can just outline from this the proof of the strong result. Proof that that the automorphism group of z to the a to the z to the d plus 1 does not embed in the automorphism group of d to the z to the d. What is the proof? Well, you just observe that the simp of the ought of a to the z to the d plus 1 at n is greater than. So by the way, I defined simp with respect to finitely generated subgroups. So actually I should write here some g, which is a finitely generated subgroup of. So I find some finitely generated subgroup where this happens. So the simp of some g, which is a finitely generated subgroup here, is greater than or equal to this. That was what the theorem actually says. I forgot that for simp you need a finitely generated subgroup, of course. Okay, you have this, and this is d plus 1, and this is strictly larger than exponential in n to the d, and this is roughly the this is an upper bound on the simplistic growth of a to the the automorphism group of a to the z to the d at n. So that's the proof. So this group cannot embed here because here you even have a finitely generated subgroup whose simplistic growth is greater than the one here. It's easy to show that simplistic growth gets larger when you pass to a larger group. So that's why. this works. So I will just draw a little square. This is the rough outline of the proof. Of course, the hard part is the proof of this. So that's a very complicated construction, but I don't have time to go into the details of that. Okay.
Thank you very much. Okay, so in case there's any question, here there is, like, as I showed you before, there is the transmission. In case anyone has any question, we have a couple of minutes. Well, I wanted to ask you about because you said you proved something also for the free group, right? That the free group was there. Did you use a similar argument for that?
Yeah. So it's even I have a couple of exponential here. For the free group, you have that the simp of sum G, which is finitely generated in the automorphism group of H at the F2, the simp of that is greater than or equal to exp of exp of exp of n to the alpha, where alpha is something positive. Okay, so you have this kind of doubly exponentially stretched exponent. I don't know what to call this kind of function, but this is far larger than any of these.
Okay. Sure. Very nice. So is this paper already in archive or not
yes,
yet?
This is in archive since spring.
In spring. Okay. Yeah. Great. So we can have a look as well later. And another question is, so in a way you are showing these embeddings. You are looking if there exists, an injective homomorphism, right, from one group to another. What about? Do you think it makes sense to ask if there is like a surjective homomorphism from one to another? Maybe if it's a factor group, right? One of the other. Have you thought about that or?
So actually, no, not really. So, but I can say in general that we understand factors very little. So we have very little understanding about factors.
Yes. Okay. Yeah. Something because actually, I remember this is something you correct me once in one paper, like a while ago, that we were working on showing that the endomorphism monoid is not finally generated, and we were using some surjective homomorphisms that were going to the full shift, but over the quotient, basically, and showing that there are always surjective homomorphisms. But then this doesn't restrict to surjective homomorphisms of the automorphism group when you want to restrict them, and then we couldn't. You are stuck. You cannot use the same argument for the automorphism group as you use it for the endomorphism.
And that's actually another interesting question. I mean, in principle, there could be some. Sometimes I've dreamed that for some crazy groups, the automorphism group could be finitely generated, or maybe the commutative subgroup, but I have not been able to show that, but somehow.
Yes, would be nice. Okay, well, thank you very much again, Ville, for your time and for your talk, and thank you everyone for attending the talk. Thank you. So see you later. Thank you.
See you later. Bye.
Bye.